A spherical snowball is melting in the hot Houston sun. At the moment when the radius is 3 inches, the volume of the snowball is decreasing at a rate of 4 pi cubic inches per minute. How fast is the radius changing at that time? Before we can do any math, we need to identify what equation we need to use for this problem. The clue that we have a spherical snowball tells us that we are working with the equation for the volume of a sphere. We know that it is the volume because the volume is decreasing. So the volume of a sphere is 4/3 pi r cubed. You can tell that this is a related rates problem because we have a volume changing with respect to a time measurement. After we find the equation of what we need, what we're working with, the volume of a sphere, the next thing we need to do is write down what we know. And that involves working with these numbers. We know that the radius is 3 inches. We also know that the rate that the volume is changing is 4 pi inches cubed per minute. And since this quantity is a volume over time, this is what we call a rate. And we will need to set that equal to dV dt. We have the rate changing with respect to the time changing. The volume changing with respect to the time changing. The volume is changing with respect to minutes. That's how we know we're working with a rate. That is all the information we know. The next step is to write down what we are trying to find. That is usually in the last statement or question. How fast is the radius changing at that time? So we are trying to find dr dt. Since we are working with two variables changing with respect to time, we will need to take the derivative with respect to t. And this requires us using implicit differentiation. When we use implicit differentiation, we will be taking the derivative of both v and r with respect to t. And in this case, we will just be using the power rule, as our variables are only raised to a power. So as we take the derivative, the left side will be dv dt, and that will equal 4/3 pi times 3r squared. And since we're taking the derivative with respect to time, and implicitly, we need to add on the dr dt. Now we will do a little bit of simplification in that this 3 and this 3 can cancel. So we're left with dv dt equals 4 pi r squared dr dt. Now we can use these values over here of the radius and how fast the volume is changing in our equation over here, so we can solve for dr dt. So I will substitute in 4 pi for the rate at which the volume is changing, and that will equal 4 pi, and r is equal to 3 inches, so I'm going to substitute 3 in here. dr dt. And before we get any further, I need to correct something. And that is the idea with this volume of the snowball is decreasing at a rate of 4 pi cubic inches per minute. Since the volume is decreasing, we need to call this rate negative 4 pi cubic inches per minute. So when we substitute that in, this will also be negative 4 pi. Now to solve for dr dt back in our equation, we just need to divide both sides by 4 pi 3 squared. When you do that, you get that dr dt is equal to negative 4 pi over 4 pi, and 3 squared is 9. From here, you can reduce 4 and 4 to 1. You can also reduce pi over pi to 1. So this leaves us with negative 1 over 9. And the radius is in the unit inches. And we need that because the radius is changing with respect to inches. And the way the time is changing is by minutes. So we can say negative 1 inch per 9 minutes. Or we can say negative 1 over 9 inches per minute. That is how the radius is changing with respect to time.